So this week is pretty fast, right? The Monday is a break and Wednesday was exam. Now it's Friday. So here's the feedback, okay? So some of the problem, you guys did a really good job on that, so I won't really dive into it. For example, problem number 1, it's almost 100%. For 90% of you guys, got 100%. Number 2, I think 20% got 100% right, and the rest are not exactly 100% right, but I also give you guys a lot of partial credits on that. So, you know, this line is the perfect solution to this problem. Since I told you guys in the hex mode, right? If you use the binary mode, I also give you partial credits. But the solution is 1C, 7C, okay? And to set these digits, you need to do an OR logic and put a 1 at these locations, and all the rest of the digits will be zeros for the mask. And then you write it down, right? Just write it down here, and then you divide it into fours, groups, and eventually it becomes 1C, 7C. And so it has to be data, do an OR logic, bitwise OR, make sure it's a 1 bar, not 2 bars, bitwise OR, and then put it back to result. Any questions by far on that? And the next one, shifting, right? Shifting. I have the same problem on the static guide, and we did that for one of the in-classes and homework assignments. So shifting to the left by 1 digit is multiplying by 2, right? And then plus 1, so you are getting equivalent value for multiplying by 3. So shift to the left by 1 digit is times 2, right? And then plus 1 more time. Plus itself 1 more time. Okay, you need to, since I told you this is, the result is still within 16 bits, so it's not overflowing. You just declare another variable here as a 16-digit variable. And this one, I changed the schematic a little bit, and it's a trap, and 90% of you guys just jumped into the trap. It's a very simple one, right? So the circuit was very similar to the ones from the example, right? And now this pin is put down, not put up. So at the very beginning, it was 0. So this has to be false. So it can stay there, right? And then someone pushes, it's being put up. It's being shorted, not put up. It's being shorted to VD. And it will stay here, right? And then you release it, it will jump out from this while loop and do this addition here. This one, 199, if it's a 200, it becomes 0 to 55, and will give you 56 counts, because this is 1 more count, so it's adding 1 more to it, 1 more digit to it. It's asking for count, not I, okay? So count is a variable here, so count will be 57, not 100 something, okay? And for this one, it already shows you this is the F here, so it's a character. It's definitely a character type. It's also a character type because uppercase and lowercase, they are both characters. And because the Arduino is different from other microcontroller platforms, and in that case, you have to put a setup buffer first. I have this in the examples since the beginning of the semester, right? So you have to declare a buffer first, and have to do a spring F and print it to the buffer first, and then do a serial begin printing. Because the Arduino printing, the serial dot printing line cannot apply any specifiers in it. So you have to print everything to a buffer first, and the buffer is also a character type, and then directly print on the buffer afterwards. So I have to pre-print that character with the specified format into the buffer, use a spring F, and then do a serial print directly from the buffer. Okay, that's how that works. I've been doing this for millions of times, and so that's the way you do it, different from the C++ module from the PC, right? We'll program with the PC. This one, a lot of guys didn't divide it by 2, so it's actually a half period. I think maybe 50% of you guys didn't divide by 2, but I still give you partial credits on that. So you find out this time, and then this one, the prescaler, it's divided by 4, right? So this prescaler is dividing the frequency, not multiplying. I think 30 to 40% of you guys just multiplying 4 by 16 mega. That would be nice if you can directly increase the frequency over there with the microcontrollers, but it just doesn't work that way. Okay, don't multiply. It's difficult to increase the frequency because this is already given, right? You cannot really increase it. So it's always dividing from the given frequency. Usually, the original frequency is the highest frequency you can do on chip, and then you divide from it. It's very challenging to increase the frequency given the hardware. You know, there are a lot of limitations of the hardware, like time delay, the technology being used. Like the Arduino ones are usually like 350 nanometer technology. It's just a little bit smaller compared to the 500, the C5, which is a 40-year-old technology. So it's really, really old technology for Arduinos. It really cannot run at higher frequencies. Okay, so this is the time, convert to seconds and times the frequency by per second. So you get a second, the time canceled out, and eventually give it the counts. So you guys are, I've never seen this solution. So did I calculate this wrong? You can double check, but the way to calculate it is correct. It's just depending on the calculation. I see a lot of 2220 instead of 2240. I don't know how that.
I think it's just rounding because.
I was rounding, okay.
Yeah, because for that I got 0.55
yeah.
seconds.
Got you, okay.
So if you round it to 56, it probably.
Okay.
Like,
Yeah. Okay. Yeah. I give it the credit. That doesn't matter which. If it's very close to this number, I give it the credit. Okay. I'm not taking any points off for that. And for this one, the first question is just asking what that is. I have everything appended to it. And this guy is bit 3, bit 4. It's really happy to see a lot of you guys are using the Arduino sort of format of programming. You know, one shifted by that register since I have everything appended. That's definitely correct. I give you that credit. But if you are using a binary number or hex number to do the same job, I also give you the credit as well. Okay, so this is to clear these bits, and you just need to put 2 zeros at these 2 locations, and for the rest of the bits, you just give a 1 to it, right? So and then you do AND logic that will clear these 2 bits specifically, and leave the rest unchanged. Okay. Next, starting at this count in the register, I have to use 2 to the 16 is to minus that number to get the rest counts. It needs to go through instead of directly using 30K. I think maybe 20-30% of you guys just directly use the 30K. So I have to use this minus this one and then divide it by this one. Also, I see a lot of people directly use the 16 mega times 4. Keep in mind, never do that anymore in the future. It's going to be divided by 4, not times 4. And this one, this keyword, nothing fancy there. Name of the registers, you know, the location, how to enable interrupt, right? How to enable interrupt. So very routine operations. And this is for the PWM, okay? So the mode 14, you can directly find the information from the appended information, the tables. Nothing fancy here. And the state machine programming, it's just directly from the homework assignment, unchanged. Okay, so this code, I deleted a lot of redundant stuff like the scale note, the nested referencing for the notes, right? So I directly just use a song which is given. So it's gonna be notes bracket with all the note index in there instead of the code from the homework assignment, right? So in that case, you directly use this one to access all the notes, okay, instead of the one from the homework assignment. Here, and so it's 1 point for each line, okay? If you are losing 2 points, which means you have 2 lines are incorrect. And then here, right, so play note to be true, and duration as well, so I don't have a pretty long name for that. It's just duration and note index. Okay. So I left this blank the night before the exam, and eventually I find out, I want to be nicer, so just keep those solutions over here, so I have something to look at, so I can finish the previous ones. But eventually, I think the timing, the control of the timing of the exam was pretty good. I think 1 of you or 2 of you turned it in 5 minutes before the end of the exam, and 80% of you guys turned it in on time. So I think it was good. It was a good one. Any questions on this? No? Okay.
Will the final be cumulative?
I think so, because it's 2 hours, right?
Right.
Yeah. We only have 3 tutorials to be covered. I think maybe 40% from these ones and 60% of new ones. Cool. So please bring up your in-class number 8, and we'll talk about IRs.
I don't think we got any. That's 3.
I gave it to you. I did. In-class number 8. Take a look at it. Yeah, I printed off 15 copies, and I don't have any left.
All the papers look the same.
When you learn more about this topic, I think you will feel that programming microcontroller is just a treat compared to other technologies. It's just so repeatable, and if you follow the certain routine, you program and put the code into the IDE, and you download it to the microcontroller, it starts working for most of the cases. And debugging the circuits, troubleshooting is accessible. You look at the pins. There are so many tools available in the lab, like the oscilloscopes, multimeters. Everything's accessible. You always get it to work if you know how to do it. Okay. IR. This is a pretty exciting topic, and we'll cover 2.5 weeks if you look at the schedule here. So today we'll start this topic, and Monday we'll run more about it. There will be an in-class number 9, and this is homework 7. There will be 3 tasks. Task number 1 and 2 will be due Monday, the week after next. So a little bit heavy load alert here. Make sure you don't start working on it until the end. The reason for that is I'm not giving you a complete template. So I'm asking you guys to declare the variables by yourself, but I do provided a lot of information over here, the pieces of the code snippets. For example, like these ones, right? The functional blocks. But you have to start building the code by yourself. So it's a bit more than a week to work on it. 2 weekends and 1 week. It's about how many days? 10 days, from 17 to 27, right? I think it's doable. And then task 3 is more difficult, so I'm gonna give you another week to work on that. And But at the same time, you have another task the week after next, which is the PCB design. So that's a last mentally challenging task. It will give you some baby steps to take. And the expectation is by the end of the semester, you guys will be the experts on PCB design and prototyping microcontrollers and put on the PCB, including soldering. Will be really beneficial for looking for jobs in the industry. And so the PCB is due the 7th of November. The reason for that is we cover IR, we cover IC card, and maybe a little bit microphone on the board, and I think that's all the modules available on the board. So in that case, for the course project, when you are designing your PCB, you can really think about what kind of modules you have to learn in the semester, and you want to put on your own PCB. Okay, you can definitely add more modules like the accelerometers and display modules, which are pretty simple, and a lot of other things. But I do hope that you can get your PCB design file by Friday, but not too much time, not too much delays after that, because it takes time to fabricate the PCB from the manufacturers in China. So, all right, a lot of fun stuff to work on. I think the same way. Do you? It's exciting. Okay, so this is a really exciting project, I promise you. IR transmission and reception. So it's like the remote. All these ones are using this very similar frequency, right? So when you press the button, it emits IR signals. It's a light signal, pulses, and that signal is being programmed in the PWM format. Okay, and for the one we have on the board is a 38 kilohertz PWM, and you can program it into different frequencies and with different duty cycles. But given here's the one example, a typical example over here. Okay, so the first thing you need to know that is for the IR signal, the pulses, light pulses, is being triggered by an electrical signal from the board, and the electrical signal will trigger that LED to blink, and it blinks in a certain way to send out light signals like this. And whenever the light signal is oscillating, the decoder on the board is receiving a 0. It's really interesting, right? But it's a decoder. You can design the decoder in whatever way you want it to be. But the decoder for IR, transmission and reception, is that whenever it's a pulse, it's a series of pulses, the decoder is going to output a 0 to the board. That's the first thing you need to know. Why? I don't know the answer, but that's how that works. And whenever you, if the emitter is not sending a pulse, if it's 0 or nothing to be sent, and the decoder is pulling up the signal to 1, so the decoder on the board is sending out a 1 to your microcontroller. Okay? Let's take baby steps. This is the first thing you need to know. Okay? And then let's go to the schematic of the board, of the SKY board. So that's the driver for the LED. The driver for the LED. And a lot of times we use the BJTs to drive a LED, and this is a BJT. If you didn't take analog circuit design, which is fine, but you can just recognize this device as a switch. Okay, pretty simple. It's just a switch. If you turn on the channel here, the switch here, and there will be a current flow through the channel. That's it. Make it super simple, okay? If you turn it on here, it's called the base terminal, it's a base, and the current is gonna flow through the channel from top to bottom. Does that make sense? Okay? We are not doing any calculations on the base and the beta, the current amplification. Nope. It's just turn on and the current will flow. If you don't turn it on, it's just disconnected. So the top LED here is disconnected from the ground, and there won't be any current flowing through the LED, and it will be off. It'll be off. Okay? So now, here's a little jumper on the board. if you look at the PCB, it's a jumper here, the JP5, which connects PL4 pin of the microcontroller to the resistor here, which directly connects to the base or the switch. If you jump it, which means you are actually shorting this terminal directly to the pin of the microcontroller. And if you do a digital write, you can do whatever you want to it, right? This is a digital signal. Then you can control this pin on and off. So first thing, you have to jump it. If you don't jump it here, and you can still control it by connecting a long jumping wire from one of the pins of the microcontroller to this pin, right? It also works. But I have to figure out which pin is that, the bottom or the top. Let's take a look. Bottom or the top? Here. Number 2. Bottom or top? Of the 2 header pins. If you don't want to use, you want to tell me, hey, Dr. Lee, I don't want to use PL4 to control it. I want to make my project a little bit more difficult. It's too easy. Your tutors are too easy, right? You want to have a jumping wire from somewhere else, from one of the other pins, and to connect it to this terminal so you can control this space and this switch, right? You don't have to use this jumper. You can use the jumping wire from somewhere else. So where, is this pin at the bottom or on the top on the PCB? Bottom is over here, number 2. See? Sorry, it's a really simple question. See, JP8, right? JP8 is bottom. Okay. So if you don't use a different pin, you just want to use the designated pin that I put on the PCB. You can directly put a little jumper here, and then pin PL4, which is pin number 45, will be controlling that switch. Okay, so pin 45. If you go to, I already showed you here. Pin 45 on the pin out map is called OC5B. What is that? OC5B. What is OC5B? What does that mean? What kind of information can I get from the name? See, OC5B, where is that? Pin 45. 45, where's 45? Here, right? It's a PWM, so that pin is shorted to a PWM module in the chip, right? And the output is called OC5B. So that's PWM. Which timer is controlling it? Which timer? Timer 5 and module B, right? Okay? You don't have to use timer 5. You can use any other timers. You can see here, 46 is OC5A, right? It's a timer 5, module A. You can also use, just find out the PWM pins, right? So this is also a PWM. This is OC3A, is a timer 3, module A. I don't really care. However, the example is based off the module 5, so timer 5. Okay, scroll down to this figure here. Here's the IR LED. So IR LED is the IR emitter. It emits infrared signals. You couldn't visually see it by your naked eye. You don't want to directly stare at the IR. It's actually a hazard. It's a light hazard. You'll see it's running like 0.4 amps through the LED, so it's actually super strong. But your eye couldn't tell. And you are staring at it, actually it's emitting super strong IR lights. It's hurting your eyes, your nerves in the eyes. So never directly look at it. However, a lot of times you can use your camera to see if it's really being turned on or not, because the camera can really see a little bit blink of the IR light, can detect it, but your eye cannot. So usually, you know the spectrum of the lights? Did you know that in physics? What's the visible range? Visible. This is the wavelength, right? In nanometers. Here's visible. What's the visible range? Even though it's the microcontroller stuff, but you need to know since you are dealing with all the sensors and light sensors, right? What's the visible range?
380 to 700.
Yeah, 400 to 700. A little bit more over there, but it's getting dimmed. So anything higher than 700 is considered, what's that called?
Ultraviolet?
No, infrared, right? And this is
Far ultraviolet?
UV, right? UV. Which one has more energy? This, right? Which has more longer wavelength? This. Okay. So the IR we are using is like 900 something nanometers. So it's definitely IR. It's in here. Both are visible, but this is here. Invisible. I'm sorry, invisible. So that's the LED emits IR, 900 something nanometers. And when you toggle this pin, and this current is being turning on and off. So it's actually this is being toggled. Okay, and 2.2, this was calculated depending on some of the parameters. So we're not going through that. But the thing is, you can see the resistor here is pretty small, which tells you that it's probably going to run a lot of current through that. And high current means high intensity of the light. Okay, again, don't directly stare at it if you are expecting that something's being turned on and off. So you control this guy to control this guy's duty cycle and frequency, right? Since you turn it on, this guy turn on, you turn it off, this guy getting turned off. Make sense? That's how you emit IR light through this pin. And given that if you send an electrical signal on and off, it's from 0 to 5 volts, you're toggling this guy, and it's going to emit light pulses. Keep in mind. So whenever you toggle this guy, this LED will emit pulses. However, we cannot plot it because it's not electrical pulses. It's just the pulses of lights. It's going to be in the air. And that thing in the air will be received by this receiver. It's also on the board. It's just next to it. That little black module is next to it. You can see the little bump in front of it, right? And that thing will receive the light pulses. And if it's a 1, it will output a 0. If it's a 0, it's going to output a 1. You're asking why? We'll see why. But now, don't worry about that. It's just something can differentiate the different signals from the emitter, okay? As long as it can tell the differences, it's fine. It's just digital, right? And the outputs, because this guy is being shorted to a, okay, you can see here is the 3.3 volts, right? It's a 3.3 volts. Does it matter? Does it matter? Here's the 5 volts pulses, 5 volts pulses. And the reason for that is our Arduino is sending out the signal as a 5 volts logic, right? So 5 volts logic to this pin, and I'm also doing a VDD at 5 volts, and then this will be a pulse electrically, but whenever it emits light, it's just a light pulse. There's no like voltage and references. It's just a light pulse in the air. And that light pulse will be received by the receiver here, and I'm using a 3.3 volts because the device requires a 3.3 volts VDD, but probably 5 volts will damage it. Anyway, so that pulses or ground will be received by the sensor, and then eventually it's giving a response of 3.3 volts logic, 1 zeros, because this guy is being powered up by 3.3 volts. That's why the output will be 3.3 volts logic. And 3.3 volts is higher than 2.5 volts as the threshold voltage as a logic 1 of Arduino. So that's why this 3.3 volts 1 will be recognized as the logic 1 for Arduinos. So you can directly short this guy to your Arduino pin. And 3-point servos 1 will be recognized as logic 1, and ground will be recognized as logic 0. Any questions by far? I'm answering any of the questions on the sheet. Not yet. So number 1, what's the frequency, typical frequency of the for the decoder? The decoder. 30K kilohertz, 1 point. Number 2, wavelengths, typical wavelengths of the light, IR light. 950. What's the peak emitted wavelengths of the LED? 950. Why? Where do you figure that out?
If you keep scrolling down on your thing, it's the next one.
Great. See here?
That's the receiving. That was the next one. 'Cause that's
Oh, peak emitted wavelengths. Peak emitted wavelengths of the LED. Oh, it's over here.
Yeah, is that the emission?
Good job. Yeah. See here? It's emitted. He just runs 17 miles in the morning. You know, morning exercise is great. Keep you awake. You know, sometimes I think doing these are great because I see a lot of you guys are zoning out. So this will keep you guys, you know, paying attention to the class. Next, why we want to use pulses for IR instead of directly 1 zeros. If you look at the signals here, pulses, right? Pulses. Pulses being recognized as 0, 0 recognized, which doesn't matter how you decode it, doesn't really matter. But why you want to use pulses? So first, because it's emitting something in the air, to the air, and you want your IR light to be super powerful. Imagine I'm doing this remote, right? I'm pointing to like the wall and reflects to the receiver over there, over the projector, and still respond to it. So it has to be powerful, okay? Which means you are running a lot of current through the LED. So if it's running a lot of current in the amps level, you can see it's like 0 point something amps. It's a lot of current. So you want to really keep it on for the whole time, for the entire time over here, which will probably reduce the lifespan of the LED. So, but if you're doing a PWM, reducing the duty cycle of it and doing pulses, will definitely protect the LED. So it's also sending pulses, but it's not really keeps it on all the time. It's not generating a lot of heat. It's also saving, increasing the lifespan of the LED as well. Okay, that's the first thing you want to do it because the first is the current is too high, right? And second, using pulses, it's sending a very specific light signal to the receiver, making it very different from other noises from the ambient light. Okay, because you have other lights are also emitting signals. It could be ones, could be zeros. If you are making it very different with a certain frequency of oscillation, you can reduce a lot of effects from the ambient lighting. And another reason for that is you can change the duty cycle, you can change the frequency, you can customize everything in order to reduce the crosstalk from other IR signals. For example, the remote here, and I want someone is keep pressing the remote of the TV of the projector. At the same time, I want to also programming my board as well at the same time, right? So you want to differentiate them by using different frequencies and duty cycles. If it's just a 1 0, you couldn't really tell, right? So the 3 different reasons. First, current's too high, you want to protect it. Second, you can reduce the effects of ambient light. And third, you want to create a unique frequency to avoid crosstalk from other devices.
It's called crosstalk.
Crosstalk. Talk. Number 5, if you look at the curve over here, this guy. See, you can pick up all different duty cycles. However, a different duty cycle will give you a highest current that it can run through the LED. For example, over here, if I'm using a 10% duty cycle. Oh, one more thing here. For our decoder, and this is 38 kilohertz. Okay, and this duty cycle here doesn't have to be 10%. Doesn't have to be. I think 10%, 15, lower than 10%, 5%, all of them work for the decoder. So, however, here the one we are going to use is 10%. Now we find out that number from here, since 10%, you can see it's pointing to this curve, and the maximum is like 0.4 something amps, and that current is calculated from the circuit, from the schematic. It depends on the values of the resistor and the device you are using here. But we are not getting into the calculation because a lot of people are not taking analog. See, it's determined by this circuit, the resistor values here and here. It's giving you that current. But you can see that for question number 5 specifically, it's asking you to put the parameters for what? For T. Right? You can see TP. So TP is the duty value, and T is the period, and TP over T is the duty cycle. So 10% duty cycle is going to be, D will be 0.1, right? D will be 0.1. And if you calculate the timing for the period, since we know it's 38 kilohertz, right? So it's 1 over 38 kilohertz will give you the period. Okay, you can calculate it. If it's not given on tutorial, or maybe it's given, I don't know. It's Friday. And then you do a 10% out of it, right? So to find out TP. And the maximum current you can run it through the LED is going to be 0.4 something, 0.43 amps probably. So since we're not doing the calculation of the BJT's current, so it's just letting you know that the scale of the current, which is very high, right? It's several hundred milliamps just for the LED. It's actually really high. It's very power consuming. Any questions by far? Number 6. 10 degrees off from the center. 10 degrees off from the center. Where's that curve?
It's the one right below.
Yeah, this guy. So that tells you where you want to place your decoder, right? So if you place your decoder really far away from it or on the back of it, you're not actually getting anything. Why do you put on the back? Since you want to receive the IR light pulses, right? So you want to put it. So what I did is I just directly placed it next to it. I'm expecting reflection from the objects in front of it, right? But actually it's not super sensitive because the light is just so strong. You point it to the wall, it will still reflect it back to the receiver, right? It's really reliable. It's really interesting technology. Okay. So for 10 degrees, you can tell that it's actually attenuating by almost 50-something%, but you can reform it, maybe 55 or something. Start getting 45% of this intensity being received. Okay. So imagine this is like shooting to the front, right? If you directly put it in front of it, it's 100%. And then at the different certain angle, these are the radiation, intensity with percentage of it. Okay? Number 7. PL4 is a pin, right? Which pin drives the IR LED light? It's PL4. It's given here in the curve, in the schematic. See, it's PL4. PL4 is number 45. So that's number 45 on the board. And also, what's the name of it? It's OC5B. OC5B. What's the register behind it? OC5B. What's the register behind it? OCR5B, right? What's the top? ICR5B, okay? So these different three names. The top is ICR5B, which answers the question number 9. So it's ICR5B, OCR5B is a, is a register, right? It's a register for the duty cycle, defines the duty value, which is question number 10, part of it. There will be pop quizzes in the future, okay? Keep in mind, I'm just directly asking you, ICR5B, OC5B, OCR5B, what are they? Not too many, just 3 names. Just 3 names. I can remember like 15 names in the class. You can remember 3 names of from the tutorial. What's the bottom one? Which one?
You said the top and the bottom.
Oh, the top. I didn't ask for the bottom.
Oh.
I didn't. Number 8. Because the IR has a significant time delay, so it's not super fast, regardless of transmission. So definitely, you are not using IR. Don't propose a project saying like, I'm gonna use IR to transmit the video. Never. So IRs are just doing like bytes, right? Just byte by byte. Just code. Okay, just code. And if you want to do an IR transmission, and usually the baud rate, right? The baud rate is usually like 1200 or 2400. For task 1, we are using 1200. For task 2 and 3, we are using 2400. So what does that mean? Okay, it tells you that it's a 38 kHz of the PWM. It's actually every individual one here is 30. So these pulses are 38 kHz. Not this. Does that make sense? It's very confusing sometimes. This is 38 kHz, not this. Okay? And this is what? This is 1200 bits per second for task 1 and 2400 bits per second for task 2 and 3. You can customize it, whatever you want to use, actually. Why? Because we are using this output from the decoder as a UR input. That's why it becomes really fun. That's what you want to put on your resume, okay? You can directly write a UR driver by yourself. Okay? You can touch the very bottom of UART. Super fun. Here is the baud rate of the UART, and this thing, if you took signal processing, you know this is, sometimes they call it an envelope. Okay? If you didn't take signal, you just know it here, right? It's an envelope. Right? So it's actually covering the major frequency of the whole thing here, right? As the secondary frequency here is, but it's lower speed. Okay, so this output from the decoder is being fed back in, because the thing is, you send something out to the air, and the receiver receive it and respond with a certain digital signal with a certain frequency. Okay, now you need to read it. Because it's encoded, right? So now when you read it, you need to know the frequency of all the bits. But what's the frequency you want to use, right? So there are multiple different communication protocols available on the chip, but however, the easiest one will be UART. So we are going to use the UART to receive the signal from the output of the decoder. And the UART protocol is like this. It's probably the easiest one you can learn. Okay? Let me draw it here. Wouldn't really do too much over here in the class. One lecture. TX, RX, that's a transmitter. RX, TX is a receiver, communication, right? TX, sending, receiving, sending, receiving. Okay? So, how do you start the conversation or communication? It's always toggling. When do you know that the transmitter is start sending the data instead of just the noise or holding something like a 1? Because data is 1, pulling it up is also a 1, pulling it down is also 1. How do you know that one is a signal, not a VDD? So you need a protocol. That's why we need a communication protocols, like handshake, right? So now for UART, you guys are lucky because it's super simple, okay? So TX, when TX is sending, before it sends, it has to be 1, always 1, okay? Has to be always 1. Whenever TX is telling the receiver that, hey, guy, I'm sending something to you, it pulls it down first. So the receiver is detecting that, right? It's always 1. Detecting, keep sampling, and whenever it's being put down by the transmitter, it knows the next one will be a starting bit. So this will be the start bit. So the start bit of the UART, it could be an interview question, okay? So what's the start bit of the UART? It's logic 0. It's logic 0. And after that, it will start sending data after that, okay? And whenever it's done, it will pull it up to 1, okay? Pull it up to 1. So 1 will be the stop bit. So the data here is a byte. It's 8-bit. So the question on the in class, where is that? It's question number 15. In UART transmission, is that TX or RX pulls the voltage down to 0 as a start bit? Who pulls it down? Who? Which? TX. TX pulls it down. Jesus Christ. So, spent 5 minutes to explain everything, didn't work. But when I tell you the answer, like, you can see your heads are down at the same time. But the TX pulls it down, right? And then whenever all the bytes, all the bits in the byte are getting transmitted, which pin pulls it up as a stop bit? TX as well, right? TX pulls it down and pulls it up. 2 more minutes. Number 17, in your transmission, how many bits are being sent if the data length is a byte? How many? 10. You got a start bit and stop bit, right? So you got a start bit as a 0, put it down to 0, and the stop bit pulls it up to 1. So in the middle will be the 8 bits. So you are transmission using the 10 bits. Number 18. You are saying, hey, the UART, the look at the schematic. Here. We know that the USB communication, the serial monitor, is communicating with your disconnected from the network. Anyway, so we'll keep working on this on Monday, and that's it. Any questions so far before we call it? No?